And we're starting today by a topic which will become a useful tool for us in a few minutes. But it's also a very useful tool in itself. It's called Cramer's rule. Now, what's the idea? Well, the idea is Cramer's rule is a shortcut way of solving a system of equations. So like 2 equations, 2 unknowns. And we've talked about this before. You know, we have these methods, and we can sort of be creative and say, if we do things right and we combine, things cancel. Well, Cramer's rule is just saying, well, let's just jump through and get an answer. And in particular, the answer is going to be written in terms of determinants. Okay, so where's our starting point? Well, we have 2 equations. So these a's, you should think of as being coefficients. The x1 and x2, those are what we're trying to solve for. So we have would have said something like, 5x plus 7y. The a's are the 5 and the 7. The x1, x2 are like the x and the y. And over here, these are the values we want them to be. Now, as often happens in math, we try to say, well, what's a nice way to condense this? So what we do is we gather these and write them in these tables. Now, this first table, we'll call it capital A. These are our coefficients. So A1, A2, A21, A22. See, like A11, A12, A21, A22. The second one is our variables, what we're trying to solve for. So our x1, x2. And over here is the values that we're supposed to get out. Now, if you're familiar with the way that matrix multiplication works, and we will talk more about this in the next few weeks. And yes, we're going to do a lot of stuff with matrices in the next few weeks. That's actually like the next 3 weeks of the class is matrices. So if you don't like matrices yet, you will. You will. That or you'll have a hard time. I don't know, one of those two. But the way matrix multiplication works is you go along along the row in the first one, down the column in the second one. So you'd say A11 x1 plus A12 x2. So boom, boom. And that matches with the B1. A21 x1, A22 x2 matches with the B2. So it really is a nice way to just sort of compactify that notation. Okay, so what's the rule? The rule says you're going to take a ratio of determinants. Now, if I want to solve for the x1, which I should think of being associated with the first column, because that's the first entry, what I do is I take my matrix and I replace the first column by the targets, the B1, B2. But the rest of the matrix stays the same. Downstairs, it's just the determinant of the whole matrix. For x2, similar. Downstairs is the same. Upstairs, now we replace the second column, because the second column is associated with the second variable. And we take that ratio. And there's a comment. Similar ideas holds in general. Now, when I say similar, there's actually sort of 2 ways we can go to make this say, well, what's more general? Well, one thing we could do is we could have 3 equations, 3 unknowns. Still works. Same process works. You'll just have, for each variable, you replace the appropriate column and you work it out. Life is good. But the other thing is there's nothing that actually says that these numbers inside of A have to be numbers. They could be other things. In fact, it turns out they can be anything you want as long as it makes sense to add and multiply. So they could be functions. And we'll see why that might be useful in a little bit. All right, so let's try this out. So let's use Cramer's rule to solve for x and y. And I filled in a bunch of boxes here. So give me some numbers, but try to be nice-ish.
2.
Okay, 2 is a nice number. 10. 6. 5.
0.
Not that nice. You won't believe me if it's that nice. 7. 9. All right. Now, of course, you can try this on your own with any set of numbers you want. So the goal is we want to solve for x and y. Now, of course, in the first equation, we divide through by 2 to begin with, but we're not even going to worry about that. We're going to whatever. We just take what we're given. Okay. So if we think about this in this format here, this would become our coefficients are the numbers 2, 10, 5, 7. That's our A. And then we have, of course, our variables, x, y. And on the other side, that's going to equal 6, 9. Okay, so that's... Wait, what? Did I... Yes? No? Okay. You're making me nervous. I mean, I make lots of copy errors, so that's totally believable. Okay. All right. Okay. All right. All right. So, which one do you want to solve for first? X or y? X. Makes sense. All right. So the rule for x says what? We're going to take a fraction. The downstairs is we take this determinant, 2, 10, 5, 7. And when we're taking determinants, we use straight lines. The upstairs, we're going to replace the first column, because that's the x column, with 6, 9. And the second column stays as is. All right. Well, 2 by 2 determinants, that's not bad. Upstairs, 6 times 7, 42. 9 times 10, 90, and then we subtract. Downstairs, 2 times 7, 14. 5 times 10, 50. 42 minus 90, also known as negative 48. 14 subtract 50, also known as minus 36. This is actually kind of nice. Suspiciously too nice. Well, that's okay. The minuses cancel. 48 over 36 can also be written as 4/3. So our x value is 4/3. Now, y. Okay. Well, y, the downstairs, exact same. So we don't even have to do much. The upstairs, now the difference is we put the 6, 9 in the second slot, because that's the y column. So 6, 9. And then the first column is 2, 5. All right. Now, okay, so upstairs, 2 times 9, 18. 5 times 6, 30. We subtract. Downstairs, what can we do? Yeah, we just have it up here. We might as well save ourselves some work. 18 subtract 30, negative 12. Negative 12 over negative 36 gives us 1/3. And there we go. So our answer turns out that the x and y for this particular system is actually pretty nice. It's 4/3 for x and 1/3 for y. And that's it. Life is good. Okay, so that's Cramer's rule. So this is another way for you to solve 2 equations, 2 unknowns. All right, well, we're going to use it. I guess spoiler alert. What are we talking about today? We're talking about variation of parameters. So there's a lot to digest here, and but the punchline comes up on the next page. It takes a while to tell the story. But basically, our idea is the following. We're trying to find a particular solution to y double prime plus p of x y prime plus q of x y equals f of x. Now, last time you remember we talked about the method of undetermined coefficients. And in that method, you said, look, I had to be very particular. You know, I had to have constant coefficients in my differential equation. the f of x that was involved had to be very nice. We don't have any constraints like that anymore. It doesn't have to be a pretty differential equation. Your f of x can be very exotic. But we will only go up through second order. The ideas we'll talk about work for any order, but the formulas get more interesting. So we're going to be satisfied with going up through second order. And the punchline here says what? Well, it says, hey, we have this y1 and y2. What do you notice about y1 and y2? What are they? Well, what are they solving? They're almost solving this equation, except what? What's happened? If it helps, I'm kind of pointing to things. F of x becomes 0. So what you have is you say, aha, we have the homogeneous solutions. And there should be two of them. So we're saying, if you have the homogeneous solutions, you can use them to find the particular solution. All right, so here's how we start. We say, all right, so we have our homogeneous solutions, y1 and y2. We're after our particular solution. So we make our first assumption. Assumption 1. Our particular solution looks like some function, which we call u1, times our first homogeneous solution, y1, plus some function u2 times our second homogeneous solution, y2. All right, so that's our first assumption. Now, if you remember reduction of order, it has that flavor. And that's actually not a bad thing. Like reduction of order had a very similar idea, but this one, we're going to kick it up a notch. Okay, so, well, since we're after a particular solution, we're going to have to plug it in to the differential equation, which means we need to take more derivatives. So, first thing we should do is take a derivative. When we take derivative, we're going to need product rule. So, we'd say u1 prime times y1, which is what we have here. u1 times y1 prime, which is what we have there. Similar, u2 prime times y2 plus u2 times y2 prime. And then you'll see that there's some small text under here. It says, hey, let's make this 0. So we say, okay, you can do that. Now you might say, why are we allowed to do that? This is actually an interesting question. Well, how many assumptions are we making? 2 assumptions. Yeah. We even number them. Assumption 1, assumption 2. That's a pretty good indicator of how many assumptions we're making. How many sort of, I don't know the right way to phrase this. Well, degrees of freedom is a sort of a math way to say knobs and levers, like how many choices do we get to make? We get to make 2 because you have 2 functions, u1 and u2. So you essentially have 2 degrees of freedom. And so that says, since you have 2 functions that you're playing with, you get to make 2 choices along the way. So our 2 choices were that it works. That's a pretty good choice. And the other choice is that you have some nice simplification. Okay, so we've now used up our assumptions. So everything else, we just have to say, we have to be forced with what comes after this. Okay, so since that's 0, when we take the second derivative, we only have to take the derivative of this piece on the end. So you do the same thing. Derivative of the first times the second, and that'll be u1 prime, y1 prime. Then the first times the derivative of the second, that's u1, y1 double prime. Here, the derivative of the first times the second, u2 prime, y2 prime. And then you take the first times the derivative of the second, and that's your u2, y2 double prime. All right, so we have our y sub p, our y sub p prime, and our y sub p double prime. And remember, y sub p prime only is the second part. So we say, great. Using the fact that we have our solution, we plug it in. So f of x is yp double prime, p of x, yp prime, q of x, yp. So there's our expression there. Okay, so yp double prime. What have we done here? Oh, yes. What we've actually done is we've cleaned it up, actually. Well, this is what it becomes after you simplify. So you plug it in, gather, and you see, aha, I have this part right here, which is actually coming from that part. And then everything else has like a U1 or a U2, and you gather, and you say, oh, this piece matches up here. So it's 0. And this piece matches with what's up here. So it's also 0. And so we say, great, what does that lead us to? Well, it says that for U1 prime and U2 prime, we have two facts. First off, there's this from our assumption. Y1 times U1 prime plus Y2 times U2 prime has to equal 0. And then we say, well, since that went away, we have that Y1 prime U1 prime plus Y2 prime U2 prime has to equal f of x. So in terms of U1 and U2, we've now gone down to saying, aha, we know something about U1 prime and U2 prime. But what do we have here? I know it looks weird, but what is this? Two equations, two unknowns. System of equations. We could write it like that. So the y1, y1 prime, y2, y2 prime, those are our coefficients. Our u1 prime, u2 prime, those are our unknowns, and 0 f of x, that's what we're shooting for. Well, we have ways to solve that. There's a question, it looks like.
Yeah, could you explain again why we assume that the first equation equals 0?
Because we can make an assumption. And we made it here. So you're saying, why did you make that assumption? And the answer is, because it works. I know that's not very satisfying. And you're like, well, why do mathematicians do things that way? Well, because we tried 100 other ways, and they all failed. But this way succeeded. And people are like, wow, mathematicians are smart. They always get it right the first time. No. We just don't tell you about the 100 other times. So that's why it's 0, because we can assume it's 0. It's an assumption we made. And by making that assumption, we can make progress. That's essentially what it boils down to. All right. Well, Cramer's rule. And we can solve for u1 prime and u2 prime. So, of course, this becomes, take the determinant downstairs and do it on both of them. And then upstairs, you just swap the 0 f of x depending upon which column. You might notice this expression. Remember what that is? Wronskian. Because what do you see? Well, it's the functions, y1, y2, and then it's the derivatives, y1 prime, y2 prime. So the Wronskian shows up. Now, you say, okay, great. But that's u1 prime. What do we want? We want u1. So how do we get u1? Yeah, we integrate. So for example, we can say, aha, u1 is, since there's a minus, I can come out minus the integral of y2 times f over the Wronskian of y1, y2. And similar for u2. u2 is, in this case, the integral y1 times f over the Wronskian y1, y2. And, of course, I should have pointed out that upstairs you can check. 0 times y2 prime is 0. Then here you have y2 f of x, but you subtract. Here you get y1 f of x, and then the other part 0. All right, so we can find u1, we can find u2, which means we can find our solution, because we just have to multiply u1 by y1 and u2 by y2 and add it up, and life is good. And that leads us to the punchline. Yeah, this is the punchline. So, for the differential equation y double prime plus p of x y prime plus q of x y equals f of x, and y1, y2 are linearly independent solutions to the corresponding homogeneous ordinary differential equation, then y is minus y1 of x integral y2 of x f of x over the Wronskian y1, y2 dx plus y2 integral y1 times f over the Wronskian of y1 and y2 dx. And I don't even say the particular solution. This actually captures everything. This is the entire solution. It's all there. Now, you might be looking at this and saying, my goodness, this is a very complicated looking formula. Do you expect us to memorize this? And the answer is, it's on the formula sheet. This is the second thing from our class that's on the formula sheet. The first thing was the logistic equation. So it's like, yeah. So there we go. Life is good. All right. So that's the whole thing. Now there's one small subtlety I'll point out. It will probably never come up, but there is one thing that has to be paid attention to. You have to make sure that this is a 1 in front of y double prime. They might say, well, what would happen if it's not a 1? Well, the problem is you'd have the wrong f of x. And so this integral would be wrong. So you really have to make sure that whatever's in front of y double prime is 1, so you'd first divide out. Other than that, it pretty much works itself through. So we're going to do an example. Find the general solution for y double prime plus y equals tangent of x. Doesn't sound so bad. Could we use undetermined coefficients on this problem? No. Why not? Because tangent of x can't come out of a constant coefficient differential equation. The only things that can come out are things that look like products of powers of x, exponential functions, and sines and cosines. And tangent doesn't look like anything like that. So we can't use undetermined coefficients here. So that's good that we have an alternative. Okay, so if we're solving this, what should we start with? Where do we begin? Yeah, we should find y1 and y2. Good. Because, all these things depend on y1 and y2. Everything builds off of that. All right, so y double prime plus y equals 0. So remember, these are the homogeneous ODE. So we put equals 0. Well, you probably recognize these functions. We've seen them before. What are our solutions? Cosine and sine. Yeah. This is like day one stuff. It's nice to come full circle. Okay, so we can say, aha, we'll take y1 to be cosine and y2 to be sine. Now you might say, does it make a difference? And the answer is no. You might have to fiddle with a few plus minuses along the way, but you'll still get the same answer. So it doesn't matter which one you call y1, which one you call y2. All right, so we found our two homogeneous solutions. What else should we find? Yeah, it's a good idea to find the Wronskian next because it's going to show up in our denominators. So let's find that. Okay, so the Wronskian, cosine x, sine x. Okay, so that's, right, the functions. What's the derivative of cosine? Negative sine, derivative of sine? Cosine. Okay, we get cosine times cosine, which is cosine squared, minus sine times sine, minus sine squared. Does that simplify? I hope it simplifies.
Yeah.
1. It is the 1. Good. Good. All right. Life is good. Okay, so we can now say, if we just go through and copy here, this is minus cosine x integral. y2 would be sine of x times f of x, which is tangent of x, over 1, plus y2, which is sine of x. And then we're going to have integral cosine of x, tangent of x, over 1 dx. All right, so we have two integrals. Which one do you want to do first?
Second.
Ooh, the second one. Someone is like, I see that one of these is easy. What's another way to say tangent? Sine over cosine. Okay, so if I have cosine and I times it by sine over cosine, what does that leave us with? We saw the sine. So this becomes sine integral of sine. What's the integral of sine? It's negative cosine, yeah. So we end up with minus sine x cosine x. And, well, technically, let me back up a little bit. All right, this is sine of x minus cosine x plus a constant. And I'm going to point something out here in just a few minutes. Right? So the integral of sine is minus cosine. All right, good. Now, if you're after just a particular solution, you don't have to worry about the constants. You can assume the constants are 0. But if you're after the whole solution, you keep the constants there. All right, now, that leaves us with this one. Okay, sine x tangent x. Well, sine times sine x over cosine x becomes sine squared over cosine. Ha-ha. Ha-ha. Oh, wait, no, that's not a ha. That's like, what? How does one integrate sine squared over cosine? Ooh, substitution. That's possible, but there might be something easier. Well, there was somebody who was like, hey, let's pull out a trig identity. And they said, I'm going to pull out power reduction. That's a nice trig identity. But there's a nicer one. 1 minus cosine squared. Yes. So if you think about these in parts, that becomes 1 over cosine is secant. Cosine squared over cosine is cosine. Okay, so this part here becomes our minus cosine x integral secant x minus cosine x. Okay, now we all know, of course, the integral of cosine. Integral of cosine? Sine. All right. And the integral of secant is? Someone said natural log secant. You were very close. Almost that. It's the natural log secant plus tangent. Now, if you're like, oh, how am I going to remember that? It's on the formula sheet. That's how you remember it. Okay. So, and whoops, I forgot my plus c. It's there. It's very small. It's a small constant, but it's still there. All right. So, if we write this out, what do we have? Well, we have minus cosine x minus sine x becomes cosine x sine x from here. Then minus cosine x log secant x plus tangent x. And a minus cosine x times c, which I'll just write that as c cosine x. The minus can be absorbed into the c. Here we get minus sine x cosine x and plus d sine x. Does anything simplify? Sine x cosine x does what? They cancel. Okay. What about these? What are those?
One.
This
OC plus D.
This has a particular name. Look, you're trying to do trig identities. Don't do trig identities. Think about what cosine and sine are in relationship to our original problem. These are YC. That's your complementary solution. So that's why we say you get the whole thing when you do this integral, because your complementary solution is going to pop out from these pieces. So this part right here, this is your actual particular solution. So there you go. I guess, let's see, should we write it up in a box up here? So minus cosine x log secant x plus tangent x plus c cosine x plus d sine x. That's the answer. Something that we couldn't have done yesterday, but we can do it today. Find the general solution for y double prime minus 2y prime plus y equals e to the t over 1 plus t squared. All right. In case you're wondering how it goes, I won't write it all down because we have another example to do. You start with your homogeneous problem. It's a repeated root. So you get your solutions are e to the t and t e to the t. Well, from there, you do your Wronskian, your functions, your derivatives, and your Wronskian is pretty nice, e to the 2t. Now you might say, that sounds terrible, but when we plug it into the formula y2f, both y2 and f involve an e to the t. The Wronskian has an e to the 2t. E to the t times e to the t upstairs becomes e to the 2t. So these end up canceling. So in the first integral, the y1 is e to the t. And then you'll end up with the t coming from the y2. And then the 1 over 1 plus t squared is coming from the f. So it's t over 1 plus t squared for the first integral. For the second integral, you have the t e to the t. On the inside, same thing happens with your exponential functions. The only difference is now there's not a t upstairs, it's just a 1. Well, both of these are functions we've seen many times. And this one, 1 over 1 plus t squared, it's so common, it's on the formula sheet. So that integral gives us the arctangent. Here, it's almost a log. If you put a 2 upstairs, life would be good. That's where the half comes from. So half, natural log 1 plus t squared. And then you distribute and rearrange. So they're not so bad. You follow your nose. Okay, so that's the process. Good. Good. So you're ready, right? If you see this on the quiz, on the exam, you're like, no problem. Life is good. Y double prime minus 5y prime plus 6y equals 2e to the t. Now, could we solve this using the method of undetermined coefficients? Yes. Yes. This is perfectly fine. You have constant coefficients. This is the kind of thing that we like to see in terms of constant coefficient solutions. So this one, you would probably never use a variation of parameters unless you were told to. But we'll do it just to show it works. Okay, so let's see if we can finish it in about 4 minutes, because that's about how much time we have left. We start with the homogeneous differential equation, and we are going to turn that into an algebra problem. R squared minus 5r plus 6 equals 0. Does this have nice roots? Or another way to say it, does it factor nicely? R minus 2 and R minus 3. So it has great roots, 2 and 3. So our general solution to the homogeneous part, well, some constant e to the 2t, some constant e to the 3t. And the reason we use t's is because there's t's involved in that right-hand side. Okay, so, well, we just pick y1 equals e to the 2t, y2 equals e to the 3t. At the end of the day, ultimately, the only thing that happens if you swap your order is you get a bunch of negative signs. But everything works out. So don't stress too much about like, which one's the right choice to make. It's better just to make a choice and move on. All right, so we take our Wronskian. What's the determinant of e to the 2t? 2e to the 2t. Determinant of determinant of e to the 3t. 3e to the 3t. So this becomes, when we multiply, e to the 2t times 3e to the 3t is 3e to the 5t. Yeah, you add the exponents. Subtract 2e to the 5t, giving us a grand total of e to the 5t. Just one of them. All right. Now, at this point, we make sure we have our formula sheet handy. And we write down our formula. So we have minus y1 integral y to f over, I'll just put w for Wronskian, plus y2 integral y1f over Wronskian. This is just shorthand. Okay, so for us, we just put in what the pieces are. So minus e to the 2t integral e to the 3t, and f is 2e to the t. The Wronskian is e to the 5t. And then we just go through it again. y2 e to the 3t integral y1 is e to the 2t, f is 2e to the t, and the Wronskian is e to the 5t. Well, we can pull out the constant 2, so this is minus 2 e to the 2t, e to the 3t, e to the t, all over e to the 5t gives us 1 over e to the t, or e to the minus t. Here we'll pull out the 2 again, e to the 3t, e to the 2t, e to the t, e to the 5t, all together e to the minus 2t. All right, what's the integral of e to the minus t? Yeah, it's negative e to the minus t. I'm not going to worry about the plus c. We'll worry about that in a second. So this will become plus 2 e to the 2t times e to the minus t. So the plus because there's a minus. Here, what happens? Becomes negative a half. Negative half times 2?
1.
Yes, is minus 1. So minus e to the 3t, e to the minus 2t. So if you're looking for just a particular solution, you don't need the plus c's. So here I'm just doing the particular solution. E to the 2t times e to the minus t, e to the t. E to the 3t, e to the minus 2t, e to the t. So that's 2e to the t, subtract e to the t, giving us e to the t. So this is the particular solution. If we're after the general solution, you add the pieces together, namely your particular solution, e to the t, and then plus your complementary solution. So this just shows you that yes, you can use variation of parameters even when method of undetermined coefficients might be a lot faster. All right, that's it. Thank you, and have a great day.